So we will move on to the metal transfer characteristics of the droplet from the electrode towards the workpiece. So as we looked at in keyhole, keyhole stability is already determined by the various force balances. The metal transfer characteristic in GMAW also is determined by the balancing of forces that opposes the droplet and detachment, and those forces promote the droplet detachment. Based on this force balance, the shape of the droplet that is transferred from the electrode tip to the workpiece changes. And we looked at in some of the videos in earlier slides the spray transfer and the globular transfer. The mode of transfer is entirely determined by the balance of forces that I displayed in this slide. So there are 5 forces that dictates the transfer characteristics. The first one is the gravitational forces. And the gravity when you are doing in downhand welding, the welding is done when it is done downhand. Gravity always aids the droplet detachment because gravity pulls the droplet towards the workpiece. And then the plasma drag forces or aerodynamic drag forces, that is actually nothing but the force, the plasma, the force generated by the plasma jet of an arc. So the arc is not really plasma, so but therefore in the arc welding processes we say it's an aerodynamic drag given by the force of the arc and the shielding gas that always aids the droplet detachment as well. And then the third one is the Lorentz forces. The Lorentz forces which is actually determined by the converging and diverging the electrons and ions and the basic particles in an electric circuit, and the Lorentz force also always aids the droplet detachment. And then the 2 forces that oppose the droplet detachment are the vapor jet forces. The vapor jet forces are generated because of the vaporization of your base material, and these vapors are generated and then sent towards the electrode, which always oppose the detachment of droplet. And of course surface tension of the droplet, molten droplet, it always oppose the detachment of the droplet from the electrode tip. So obviously see the force balance is nothing but so in this case the Fg plus Fd plus Fm, and if that equals your vapor forces and the surface tension, then you will have a stagnant and the droplet because the detaching forces are equaling the opposing forces. So your droplet will be in equilibrium, but if any one of the forces exceeds, obviously you will have either detachment or opposing the detachment. For example, if a droplet grows in size big enough, so obviously mgh, the gravity would pull the droplet down because gravitational force increases significantly. And Fd, again it is Fd is determined by your the shielding gas velocities, for example, or your plasma characteristics if you are doing plasma welding, or if you also have an arc force, that will also determine your aerodynamic drag force. And then Lorentz force, so obviously the another important factor that determines the metal transfer and the droplet characteristics. And the Lorentz force generally aids the droplet transfer, and if you increase the current, so you also increase the Lorentz force. So obviously you can then detach the droplets in much more smaller size where Lorentz force supersedes your gravity effect. At lower currents, you can imagine that the main important the force that detaches the droplet from the electrode tip is the gravity because the Lorentz force is minimal. So once the electrode the molten droplet gains enough mass, so it can be pulled by the gravity, and so that determines the detachment characteristics. And if in case the current, obviously the Lorentz force supersedes gravity, then the droplet can be detached with a smaller diameter or with low mass. So of course if you have a very high amount of vapor jet forces, that will also determine your shape of the droplet that is detached from the electrode tip. For example, if you have a very low current and your droplet is growing in size, in diameter, then vapor jet force can also change the shape of the droplet into globular, into repelled globular, because of the vapor jet force, vapor jet coming from the workpiece. And of course surface tension is also a function of your droplet liquid droplet composition. So that will also resist the droplet detachment. Again, that can be controlled by changing the composition of the electrode. So based on the force balance, as I already explained, which force is actually promoting droplet transfer, and we can classify the transfer in majority in 4 mode. So if you look at the free flight transfer, free flight means the droplet is transferring from the tip to the workpiece in a smooth, without any contact between the tip and the workpiece. So in the free flight mode, so there are 4 types of transfer generally observed: the globular, repelled, spray, and jetting spray. So the globular transfer, it happens for a given diameter of the electrode, for example 1.2 mm, which is commonly used diameter electrode. In a carbon steel, for example globular transfer happens at lower currents, and because I already explained when the current is lower, Lorentz force is very minimal. So the main force that actually aids the droplet transfer is the gravitational force. So you need to have a mass created. The moment you have the droplet grown its size, so obviously the gravitational force can pull the droplet in a globular format. So if you increase the current slightly, so you also generate some Lorentz force, as well as because of increasing current, you may also tend to vaporize. So both increasing Lorentz force lead to a generation of local magnetic field, which can repel the shape of the droplet from complete globular to a shape of like a shoe of a buffoon in circus. So something like this. So this happens because of the increasing in the vapor pressure from the workpiece, which actually acts opposing and acts against the detachment of the droplet, as well as the increasing current can lead to a change in Lorentz force. Locally, magnetic field can change the shape from the globular to a repelled globular. So upon attaining the mass, obviously the gravity can pull the droplet down, and which is known as a repelled transfer. And if you increase the current, so obviously the droplet transfer mode changes to spray mode. In the spray mode, you transfer the droplet and continuously, where the diameter of droplet is much smaller than what you see in globular and repelled mode. And so this happens by increasing the current significantly, where your droplet can be transferred with a very low diameter compared to the globular and repelled. And this transfer is possible by increasing Lorentzian forces. Lorentzian forces aids the droplet detachment significantly, wherein the molten droplet can be transferred in a much smaller diameter. And generally the diameter in the spray mode is considered better or for a good stability. And when you are doing a transfer in a spray mode, if your droplet diameter is similar to your wire diameter. And spray mode is generally acceptable mode if you have a very stable spray transfer, and you also have a more volume of material transferred per unit time, as well as the stability of the process can be controlled much more easily, as I already showed you in the video. And if you have a continuous spray of a droplet with a diameter similar or smaller to a wire diameter, and you can transfer the droplets to the workpiece uniformly without any spatter. And of course, because of the transfer rate, increase in transfer rate, and you will also have a very good productivity. So if you increase the current even further, and obviously you also increase the melting rate of the electrode, and you will end up melting more, and then you would also reduce the droplet diameter significantly. You will end up having spray velocity increase compared to the conventional spray mode, and you will start having a stream of molten droplets continuously transferring, and in this mode it is not generally advisable because of increasing Lorentz forces you may also have a local disturbance in the transfer, so you may also end up having a spatter, and because of these increasing Lorentz forces. So this kind of jetting spray can be used for some applications in a coating. For example, if you are doing a cladding, surface cladding applications where you need to have a very high productivity, so you can have a jetting spray induced by increasing the current significantly. But for welding applications, the most of the cases, the most preferred the transfer mode is in a spray mode, just above the transition between the repelled to the spray, so that we can transfer the droplet similar to the diameter similar to your electrode or filler wire continuously, and that transfer is most preferred. Is also known as drop spray, where you will have a single drops of droplet continuously transferred or sprayed to the workpiece when the current is just above a critical value, and that critical value is known as the spray transition current. So this graph already showed shows the influence of the welding current on the droplet diameter as well as the droplet frequency. For a given current, you can see that in the A is the drop volume is nothing but a diameter, you can say, as a function of diameter, and the other graph B is the transfer characteristic or transfer frequency. So obviously, as I explained, at the lower current, the most significant transfer mode is the globular transfer, where the gravitational force is a major force that detach the droplet. So in order to detach the droplet, obviously you need to increase the size of the droplet significantly, so that the gravitational force can pull the droplet down to the workpiece. And if you increase the current, so obviously you can also transfer with a lower diameter because of the influence of Lorentz forces. So at a given current, where you see the transfer mode changes from the globular or repelled globular to the spray mode, and thus that critical current is actually known as spray transition current. So this is an important parameter in GMAW, where in order to get good aesthetics of the weld as well as the spatter free stable welding, so we generally operate in and around the spray transition current, where we can transfer droplets within a diameter equal to the filler wire to the workpiece continuously in a spray mode. So if you further increase the current, obviously you also increase the melting rate, that will lead to the jetting spray mode. Of course, your productivity will increase, but your process stability can be affected significantly. Okay, so the ideal situation of the transfer is when the steady stream of droplets with the diameter same as the welding diameter transfers from the electrode tip to the workpiece. So that is the stable conditions we always aim for, and that happens generally just above your spray transition current. So far we looked at the conventional GMAW process, but there are some disadvantages of using a conventional GMAW process. For example, if you use a constant current of a given amperage, like in previous graph we showed 200 amperes is the mean current or the spray transition current, where we apply a constant amperage of 200 amperes. So then you may also increase the heat input significantly. Okay, so so we'll have to apply that amperage in order to get the spray transition to get stable transfer characteristics. But we may also get similar transfer characteristic instead of using a constant current and by using a pulsing. So we can introduce a pulsing in current waveforms or voltage waveforms to promote spray transition. So we can do pulsing. By doing pulsing, we can also reduce the mean current significantly. By using pulsing, we can achieve a spray transition in much less mean current than otherwise if you use the constant current. So the pulse GMAW is also one of the most attractive processes to reduce the heat input considerably, but still with achieving a spray transition. So for the automotive applications, this also used as a favorable process, because we reduce the heat input significantly by reducing the mean current. So obviously, but even if you use the mean current, because of the pulsing of the current or voltage, we may still get a spray transition achieved at the workpiece to transfer the droplet in spray transition mode. And the other development we have made in GMAW is the controlled dip transfer process, where we transfer the droplets in a short circuiting mode. During this short circuiting mode, we also significantly reduce the heat input by reducing the current or voltage close to 0, so that when the droplet is transferred, we transfer it in a cold conditions compared to the conventional GMAW or even pulse GMAW. Therefore, the heat input of the process decreases significantly, and this process is nowadays is used very widely in automotive industries, especially in order to do bracing of low melting filler to join advanced silicon steels, or even to weld aluminum alloys, aluminum and steel joints, where we can significantly reduce the intermetallic formation by reducing the heat input significantly. So we look at these two processes, and then third process, obviously the development made in the process control side, where we can control all the parameters what I explained in voltage, current, wire feed rate, and the melting characteristics just by turning a single knob and using a programmable power source. So we can vary, we can control the entire process and stability increase significantly. I will touch upon some of the aspects of the single knob programmable controlled power sources, which is known as a synergy process. And then we will wind up the welding processes. We move on to the welding metallurgy case. The first, as I had explained, the pulse GMAW. The pulse GMAW process is very widely used in order to reduce the mean current of the process, so that we can also reduce the heat input. So the main advantage of using pulse GMAW, as I already explained, so we can attain the spray transition at much more lower mean current than if you use a constant current. So in a pulsing current, what we do is, so instead of having a continuous current in a conventional GMAW, so we have a current pulsing, so where we have a pulse in current is given, for example, to a pulse current which is much higher than the conventional mean current, and then we vary the pulsing period, which is Tp, and then the background current Ib, and then we also have a background time, which is Tp. So by carrying out such a current pulsing, and because of the increasing the current during pulsing and IP, so you melt the electrode tip and transfer the droplet at this pulsing period, and then in your background period, either you maintain the arc or you can also extinguish the arc, and then subsequently when you have in second cycle, second pulse is happening, you may again strike an arc and melt the droplet and then transfer the droplet at each pulsing period. And so because of the nature of the pulsing, the mean current what you achieve in this the pulsing is sufficient to get a spray transfer. And this I mean what you get in a pulsing process will be much I mean of pulsing is much, so this is lower than your I mean in a conventional process in constant, where you have a constant current without pulsing. for a given consumable. So if you have a 1.2 mm say carbon steel consumable, if your I mean is in 200 amperes, when you have a current pulsing where your the IP, the pulse current can go up to 320 or 350 amperes, but your I mean will be decreased significantly to the range of 150 amperes. So in this case again we can also control the heat input because your the I mean decreases significantly, and therefore you can also reduce the damage you have done in the, for example, heat affected zone microstructure without the heat affected zone, and of course you can also reduce the dilution, as well as if you are doing a dissimilar welding of aluminum steel, you may also reduce the intermetallic formation by reducing the heat input. But again compared to the conventional welding process, so pulse GMAWs, we use it to achieve the spray transfer at mean currents much below than the normal spray transition when you use the constant current. So we maintain a low background sometimes to keep the arc all the time on, because if you the background current reduces to much lower, then your arc may be extinguished, and then doing reignition you may also affect the stability of the weld pool. So as I explained, because of the pulsing and the IP, the peak current induces high Lorentz forces which aids Droplet detachment. When IP is given, the peak current is given, which promotes the Droplet transfer in spray mode. So I will show you in one video. So this process again we have done it with the tandem 2 electrodes. So if you see, each electrode is actually given with a pulse current. Whenever there is a pulse, you melt an electrode tape and then a droplet is transferred per pulse, and this droplet is detached in a drop spray mode, where the droplet diameter is similar to your electrode diameter. And in this case, because we do not maintain the current higher than mean current in a conventional GMAW process, so we increase the current only during pulsing period, and then during background period we maintain a very small background arc, you may see in this video. So because of the use of both mean current and both pulse current and the background current, so we have a more stable process where we detach a droplet per one droplet per pulse, and then by changing the frequency of the pulsing we may also change the droplet transfer frequencies. So the main advantage of this process, pulse GMAW, is we achieve the spray transfer it much more lower mean current than a conventional GMAW, and because of that we reduce the heat input significantly. See, other development we have done in controlling the heat input, especially in order to minimize the damage in terms of in the materials, to minimize the heat input, and therefore we can also improve the mechanical properties of the weld by controlling the microstructure. So one of the developments recent days which is actually coming up in very widely in automotive industries is the controlled dip short circuiting transfer welding processes. So one such process is commercialized by a very famous welding company, and the trade name is known as the cold metal transfer welding, CMT. You must have heard about it. And in the CMT, the process, which is technically known as controlled dip short circuiting metal transfer process. So where we have a metal transferred by short circuiting process primarily. During this short circuiting we completely either reduce the current or voltage to a very low level, so that when the droplet transfers from the tip to the workpiece, it transfers without the influence of the arc. So the heat input of this process decreases very significantly compared to the conventional GMAW or even with the pulse GMAW, and the waveform is slightly complex, and this process is achieved both by controlling the waveforms as shown in this graph, where we have a current and then time, For example, when you have a controlled current short circuiting, where we have the arcing current which actually forms an arc, and the moment you have the droplet actually formed at the tip, then the welding electrode is actually moved towards the workpiece, and during this process, the moment the short circuiting is established, the current reduces significantly, and then it maintains at a very low current, which is known as a wetting current, and which actually used to form a penton neck of the electrode of the droplet, and then when your current becomes extremely low, and your arc also extinguishes, and then because of that process your heat input decreases significantly, and subsequently upon short circuiting, the electrode is retracted back to its original position, and during this process we also increase the current significantly, so that you form a neck, as well as the surface tension driven detachment happens, and then the droplet is transferred when the wire is retracted from the pool, and simultaneously slightly increasing the current, so that you form a neck and the droplet is detached to the workpiece. And subsequently, when the electrode is completely retracted, obviously your current is increased to maximum levels to strike an arc, and then the cycle continues to the next cycle. So the trick over here is to reduce the current once the short circuiting is happened, and upon decreasing current, so you extinguish the arc, and then droplet is transferred when the wire is retracted towards the contact tip, and during this process the current is slightly increased, so that you form a neck by the increasing Lorentzian force, and the surface tension would lead surface of the molten pool will detach the molten droplet to the workpiece, and during this process, because of the absence of arc, your droplet is transferred with extremely low heat input compared to when you have a transfer either by pulse or by conventional GMAW. So I will just show you one video of this process where you can appreciate the process characteristics. So what you see over here, so this is your arcing pace, where we have an high current, and then you have an short circuiting following then arcing, and then the moment the short circuiting happens, your arc extinguishes, and then the moment your short circuiting happens, your current becomes close to 0, and then droplet is transferred by the forces by slightly increasing the current as well as the surface tension when the droplet is retracted from the pool towards the contact tip. So if you look at it very carefully here, when the droplet is actually transferred to the workpiece, the arc is completely extinguished, and then droplet is transferred by the surface tension of the pool as well as the slight increasing current driven by the waveform. And because the droplet is transferred with a very low heat input, and this process is known as cold metal transfer, because when you are transferring the droplet is transferred without the presence of the arc. So therefore the superheating of the pool is avoided by the continuous, because of when you have a continuous arc present, then you may also superheat the pool. But in this case, and because of the absence of the high current, the arc current, you transfer the droplet with much more lower heat input than the conventional GMAW or pulse GMAW. So this process is now very attractive for automotive applications, because the heat input of this process decreases significantly, and We also have control over transfer characteristics. We can also change the short circuiting frequencies, as well as we may also introduce a pulsing between the short circuiting event, so that we can also change the transfer characteristics and the productivity of the process. So these kind of the complex mechanism, complex process parameters, variations can only be controlled nowadays by the invention of the synergy power sources, where because of the control over the input current and the voltage, as well as the wire feed rate, and using a microprocessors based the power sources, so we can independently control the wire feed systems, the current, voltage. We can measure the waveform simultaneously, and then say for example, if you look at the CMT process, cold metal transfer process, so the wire feed rate, the voltage, current, they all should be synchronized in such a way that whenever the short circuiting happens, the voltage of the system should be measured, and then the moment we measure the voltage close to 0, then we identify the short circuiting event, and then simultaneously current has to be minimized, and then the wire is subsequently retracted. So in order to control all these important process parameters, and the microprocessor based power sources are nowadays very widely used, and which can give synergy in the process parameter by controlling all the parameters independently using an input output module, so that for a given current we can achieve short circuiting. When we can achieve short circuiting, we can be calculated by the melting rate, as well as by varying the wire feed rate and the current. So we may also control the short circuiting event. And subsequently, when short circuiting, we may also independently increase the current in such a way that we form an penton neck of the droplet, and then we can also retract once you have a known amount of current given, and then we can retract it and then attach the droplet to the workpiece, and subsequently the cycle can be continued. So the development in GMAW, if you look at it, the synergy process, where we can independently vary the parameters, and we can also get the parameters measured in situ, so that we can develop the much more robust and then processes which can be used to reduce the heat input significantly without affecting the welding parameters. So with that we'll summarize this chapter. So we looked at the GMAW in detail. So we didn't look at the physics of the processes, we just looked at the important characteristic of GMAW process, and we looked at the transfer characteristics, changing from the mode of transfer from globular to repelled to spray to jetting, and how the current changes the transfer characteristics, importance of various forces balances, determining the shape of the droplets, how increasing current can change the droplet diameter from larger to smaller, and subsequently we looked at some of the advances made in GMAW process, especially in two important variants like pulse GMAW and then controlled dip and short circuiting process in a GMAW process, which are very widely nowadays used to weld dissimilar steels as well as dissimilar materials.